All right, okay, well, that makes it obvious. Okay, welcome to this week's Numba public meeting. So this week we have Ashwin Srinath from NVIDIA, who's going to talk about CUDA cooperative. And I'll hand over to you, Ashwin.
Thank you, Graham, and thank you all for having me here. My name is Ashwin Srinath. I work at NVIDIA within the CUDA Core Compute Libraries team, or CCCL for short. Mainly I work on exposing the functionality of CUDA to Python users, and Numba is a big part of that. So thank you all for all of the work that you do on Numba. We're huge fans of Numba at NVIDIA, and we use it all the time. Today I'm going to talk about CUDA cooperative, which is a set of extensions to Numba that make it faster and simpler to write CUDA kernels using Numba. So Numba, as we know, is a compiler for Python functions. It takes Python and JIT compiles it into executable machine code. In addition to targeting the CPU, Numba can also target the GPU, CUDA GPU specifically via the Numba CUDA target. You do this by using the cuda.jit decorator provided by Numba CUDA. I have an example here on the right where I'm defining a Python function called double and decorating it with the cuda.jit decorator. Functions decorated in this way are referred to as kernels, and kernels are executed by multiple CUDA threads simultaneously. And so in this kernel, double, each thread is going to figure out its index. It's going to load some input data corresponding to that index, perform some operation on it. In this case, it's going to double it, and then write the result to the same position in an output array. And at the bottom here, you can see how I'm using this kernel. I'm using it with CUPI, where I'm using CUPI to create an input array and an output array. And then I invoke this kernel using 10 threads. And each thread is going to read an element from that input array and write the result to its output array. So note here that the Numba CUDA target supports interoperability with libraries like CUPI and other libraries in the Python GPU ecosystem using something called the CUDA array interface protocol. How does the Numba CUDA target work? The compilation pipeline for Numba CUDA is largely similar to Numba for other targets, where we start with some Python code, extract its bytecode, and then through Numba's typing and lowering phases, it's translated into LLVM IR. From here, something different happens in the CUDA target, where the LLVM is translated into PTX, which is an instruction set architecture for CUDA GPUs. And this happens using an NVIDIA library called NVVM. That PTX is then linked and executed using the CUDA driver library. I'll say here that in addition to translating LLVM into PTX, Numba has recently added support for something called LTOIR, which I'll talk about a little more later. Okay, so the talk today is about cuda.cooperative. And to motivate this topic, we'll look at an example problem. We're going to talk about segmented reduction. Now, a reduction would be if you had a sequence of values like this, doing something like summing all of these values together. Segmented reduction is you divide up this sequence into segments and perform a reduction on each one of these segments individually. So we're going to talk about how to use numba.cuda to do this operation in parallel. using the GPU. And then we'll talk about how cuda.cooperative helps make that kernel more efficient and simpler to write. Before we kind of dive into the Numba CUDA code, I just want to do a quick CUDA refresher. As I mentioned, CUDA kernels, or functions that are executed on the GPU, are going to be executed by multiple threads simultaneously. These threads are organized into blocks, and then blocks themselves are organized into something called a grid. And so when you launch a CUDA kernel, you do so by specifying a grid of blocks. Each block is then going to execute on something called a streaming multiprocessor, which is part of a GPU. A GPU has many of these. And so several blocks are going to execute simultaneously on several streaming multiprocessors. Threads within a block can coordinate, like synchronize, but blocks execute completely independently of each other, and they can be scheduled in any order. As far as the memory model for CUDA is concerned, I'll just say that all threads within all CUDA kernels share something called global memory, which is the DRAM on your GPU. Whereas threads within a block have access to something called shared memory that they all share. And typically, access to shared memory is much faster than access to global memory. These are just some of the things to keep in mind as we talk about CUDA kernel for segmented reduction. Okay, so let's talk about how would we implement segmented reduction or parallel segmented reduction using CUDA. As I mentioned, CUDA kernels execute as blocks of threads. And so one idea is we have each block compute the reduction for one segment. Whenever you want to do parallel reduction, in CUDA especially, you want to do something like this tree-based pattern where you have several threads. Each thread is going to sum up or reduce a subset of your values, and you do that recursively until all of your threads have summed up all of the values. With CUDA specifically, it's important to take advantage of the memory model. And so what we have is threads within a block are going to load values from global memory, which is where the values initially reside, into shared memory. And then subsequently, the reduction steps happen within shared memory. Again, because thread access to shared memory is much faster than global memory. Okay, so this is the high-level idea for how we want to implement segmented reduction. Let's look at how do I write a kernel using Numba CUDA to implement this. So I start with defining a Python function that takes in some input values, and then it's also passed some output array to hold the outputs for each segment. And I decorate it with CUDA JIT. I start with some bookkeeping where every thread kind of figures out its position in the grid. Because we're going to be using shared memory, I also have this call to Numba CUDA shared array. This is where we'll store values in shared memory. And then every thread is going to load values from global memory into shared memory. There's a little trick here where every thread is actually going to do a small reduction step before putting values in shared memory. Next, we're going to have each thread write its result to shared memory. And next is where the magic happens, where we do this tree reduction within shared memory. That's what's happening in this while loop. So at the end of this, we have one thread that kind of holds the result of the reduction. And the very last step is that thread is going to write this value into the output array. So you have multiple blocks that are blocks of threads that are all going to do this, and you're going to end up with the result of your segmented reduction. Okay, so this is all possible with Numba CUDA today. But the problem here is that this took a lot of work. I would say this kernel is fairly complex. It's quite long. It takes the whole slide for me to write out. And it's about, in terms of function size, it's at the top end of what I would consider readable code. And this is just for segmented reduction. If we were doing something like a segmented sort or scan, things get even more complicated. And this is what CUDA Cooperative is trying to solve. It's trying to provide the pieces of functionality that you can use within these kernels to make them simpler. Before I dive into CUDA Cooperative, let me just talk about what the word cooperative is and what it means in the context of CUDA. So CUDA, as I said, the execution model has several threads that are all doing work independently. So on the right here, there's an image of two threads. Each thread has a couple of values where it's able to sort those values independent of every other thread. So thread 1 doesn't have any ideas about the values in thread 2, and vice versa. Although each thread can do a serial sort on the values it knows about. Threads aren't actually completely independent. In CUDA, you have the ability for threads to cooperate with each other. So even though I said thread 1 and thread 2 don't know about each other's values, they can, and they can actually work together to sort the values that they know about using something called cooperative sorts. And CUDA libraries provide very efficient implementations of such cooperative algorithms. I'll just say here that you can't have threads across the entire GPU cooperating together. You can have threads within a block doing that, and threads within a warp doing that, where a warp is a subsection of a block. So with this idea in mind that you can have threads within a block kind of cooperating, let's see how we can use CUDA cooperative to rewrite the reduction kernel that we just talked about. We start as before, where we have a Python function decorated with CUDA JIT, taking 2 arguments. As before, we begin with some bookkeeping, where each thread figures out its position in the grid. Now we have each thread allocating some local memory for the values that it's going to load from global memory. So it's just a small array that's local to each thread. That's of size items per thread. This next step is where kind of the magic begins. We're using this function called load, which does the work of loading values from global memory into this local array. There's something interesting happening here where the load function is actually loading more values than the size of the local array. You'll see that the local array is of size items per thread, but we're actually attempting to load items per block, number of values, into this local array. And this works because load is actually a cooperative function. Multiple threads are going to work together to load items per block number of values into each thread's local array. Next, we're going to use another cooperative algorithm called block reduce, where threads within a block are going to work together to reduce all of the values they hold in their local arrays. And finally, at the end of that, we have the result. Each thread, or at least one thread per block, has the value of the reduction for values in that block. And that thread will write the result to the output array. And we're done. You can see here that this is just like 5 or 6 actually interesting lines of Python. It's much shorter, and I'd say it's easier to read and reason about than the kernel we wrote earlier. And this is all because of the cooperative algorithms offered by CUDA Cooperative. At this point, I'll say that I'm lying a bit here there's actually a little bit of boilerplate involved that I haven't shown you, which prepares these functions load and block reduce and specializes them for the specific types of inputs that they're going to accept. But it's not much, and the kernel itself is still the same. There's no real additional boilerplate to the kernel. It's really just in preparing these functions that we have some boilerplate. I guess I'll pause here and see if anyone has any questions so far. Okay, I'll keep going.
Definitely.
Yep.
So first question is, how do we control which elements from the wider block end up in the local array? So like you have to partition, right? You're loading a bigger set into, like you're asking to load from a bigger set into a smaller local things, right?
Yeah.
So how do we partition these bigger things into
Yeah.
which goes into
So you can see that when we prepare the load device function, we do have to specify how many threads per block there are and how many items per thread there are. Now, in terms
No, I
of
know, but
which thread ends up with which values, I know that Georgie's here and he can correct me if I'm wrong, but I don't think you can predict that.
The cooperative block load algorithm accepts another parameter that is called algorithm, and this one specifies multiple ways the overarching input is partitioned into threads. By default, it's load direct. That means you'll get consecutive parts of the input fall into a single thread. So thread 0 would have 0, 1, 2, 3, etc. up until threads per block. Items per thread. But this will result in uncoalesced memory accesses. So you can change that to say, for example, loads sharded. Then you'll have different threads load consecutive elements, and the input within thread wouldn't be mapping to consecutive input in the global array. But if you need to restore this order and still benefit from the coalesced memory accesses, you can change this algorithm to warp exchange or something like this. Then the load would happen in coalesced manner, and then block load algorithm would use shared memory to reorder elements and restore the original order within the thread.
thank you, George. This is useful. So in that case, does the load function need access to like a temporary storage to do this transposition, for example?
Sorry, I'd say that's also a question for Georgie.
Yes, sorry, I was hardware muted. I was saying that all cooperative algorithms accept some scratchpad memory, and block load is not an exception. When you don't specify one, like here on the screen, we'll allocate shared memory internally in this algorithm so that you don't have to care about that. But the fact that shared memory is used is still there.
Great.
Okay. So how does this work? How are we able to use these cooperative algorithms, and where do they come from? The implementation of cooperative algorithms like block load and block reduce come from a C++ library called CUB. It's a header-only library. You can see an example of how to use it on the right. It's in C++, and it provides many cooperative algorithms. So examples are block load and block reduce that we've seen, but there's also other block-based algorithms like, for example, block merge sort, which does a sort on the values within a block cooperatively. And as I mentioned, thread blocks aren't the only level at which you can have threads cooperate, but you can also have them cooperate at the warp level, where a warp is just 32 threads that are all scheduled together for execution. But CUB is, as I mentioned, a C++ header-only library. And so how do we invoke it from Numba CUDA kernels? The devil's in the details, and the answer to this question is actually that it's quite complicated and involves a lot of pieces. I'll try to provide kind of simplistic view of what's happening here. So if you remember from the boilerplate, we have to prepare these functions like block load and block reduce. What's exactly happening when we do that? The first thing that happens is we, behind the scenes, are going to generate a wrapper device C function that actually instantiates all of the templated functions from CUB and prepares a true callable C function from those instantiations. That device function is then compiled into LTO-IR, which, as I said, is another target that Numba can compile to, but also link with. We'll talk about this in a second. But this compilation of this device function is done using a Python library called nvrtc, or wrappers for the nvrtc library. Numba knows how to take multiple LTO-IRs and link it together with the code that it's going to compile with CUDA. And this is actually a big piece of the puzzle. This isn't supported by Numba CUDA proper. It requires a patch to the linker used by Numba CUDA, and this is enabled by another library called pynvjitlink. So when compiling functions with cuda.jit, you can specify a list of LTO-IR files to include for the linking. And then when Numba actually sees calls to block reduce or block load, we define what the code gen for that is supposed to do. And what it's going to do is inject calls to the device functions from that LTO-IR. So at a high level, all of that is happening when you prepare and call these functions block load and block output from within Numba CUDA kernels. And all of this functionality is part of what is implemented in CUDA cooperative. In terms of performance, we saw that we have a much simpler CUDA kernel with really no loss in performance. In fact, I see that for larger arrays, I have improved performance for reduce in particular. I don't think I can explain exactly why we see this, but I was able to reproduce that pretty consistently. For reduce, there's not much of a difference in terms of performance, but I'll just show you in a bit more that for other algorithms, we've seen improved performance. So there's no loss in performance. In fact, we're faster when using CUDA cooperative. There is an additional JIT overhead, but CUDA cooperative maintains a kernel cache that persists across interpreter sessions, similar to Numba's built-in kernel caching. And for more complex algorithms, as I mentioned, we've seen some greater gains in both the simplicity and speed that CUDA cooperative brings. So this is for segmented scans, like cumulative sums or cumulative reductions. On the left here, you can see what the CUDA kernel would look like if we just use plain Numba CUDA. And on the right is the version that uses CUDA cooperative. Just like with segmented reduce, it's much shorter, much more concise. And we've seen it go up to 2x faster than the naive implementation. For merge sort, we have similar kind of situation where if we wrote this with just the pieces provided in Numba CUDA today, you can see that I really had to reduce the font size to even fit the code on the screen. But with CUDA cooperative, it's very similar. We just we have a block load to load some values into a local array. We have a cooperative sort, and then we have a block store to store the results into the output. And similarly for static sort. Okay, so just to recap what we've talked about so far, CUDA cooperative is essentially a collection of Numba extensions that expose the cooperative primitives provided by the CUB C++ libraries. What it lets you do is it lets you write CUDA kernels using Numba in a much more simpler and efficient way. It works by combining a few different pieces of technology together, including Numba, CUB, NVRTC, and NVJITLink. Who should use CUDA cooperative? Anyone writing Numba CUDA kernels that can benefit from the kinds of cooperative algorithms I've talked about. What does CUDA cooperative support today?
Sorry, just before we go on, I think Georgie's had his hand up for a while.
Oh, I'm sorry, I can't see that on my screen, so go ahead, Georgie.
Yeah, I wanted to comment on the performance improvement from cooperative reduction. And that's kind of has to do with the length of the code you see on the screen as well. So the reason there is a performance improvement is that we use latest hardware features like DPX instructions. We build different reduction trees that are not like binary, and then we also use redux instructions that would try and reduce a single warp value with a single instruction instead of like building this stride loop that you have on the screen. So we'll try to use recent hardware features extensively in these algorithms. And if you go to the next slides where you have code on the left, this is a naive implementation that is quite short. If you start implementing all of the recent hardware features in these kernels, it'll increase in length quite a bit. And the different thing I wanted to mention is that these cooperative algorithms also support user-defined data types. You're not limited to the built-ins you see on the screen, like ints and floats. You can actually define your own data types with Numba, and cooperative algorithms will work with that as well.
So it's, I guess, something that I failed to mention is exactly this, that when new hardware or software features come out and you have a bunch of Numba CUDA kernels, you would have to update them to incorporate these new features. But by relying on CUB, which is maintained by NVIDIA, you don't have to do that. CUB takes care to figure out what GPU architecture you have and provides the best implementation available for that specific architecture. So that's another advantage of using CUDA cooperative versus rolling your own CUDA kernels. Okay, so what's supported by CUDA cooperative today? We have some functions for both the block and the warp level. You can see them on the screen here. For block, we have reduce, scans, load and store, sorts. And for warp, we have sum specifically, sorts and reduce. We have a ways to go here. Some of the future work that's planned for CUDA cooperative is exposing more algorithms for both the warp and block levels. Supporting Windows. Right now, CUDA cooperative works just on Linux. And mainly this is because of the dependency on this PyNVJITLink library that I talked about, which in turn is supported only on Linux. There's a plan to migrate away from PyNVJITLink to something else that is supported on more platforms. This problem also blocks us from potentially upstreaming CUDA cooperative to Numba CUDA. So perhaps once we're able to resolve that, there will be a path for getting the functionality provided by CUDA cooperative to the proper Numba CUDA target. It's also not currently available on PyPI or Conda, so doing a source install is the only way you can get your hands on CUDA cooperative today, but it's very simple. It's just a pip install dot. I also wanted to mention some other work that we're doing outside of CUDA cooperative, which is another library called CUDA parallel. So just like CUDA cooperative exposes the block and warp level primitives offered by CUB, CUDA parallel exposes the device-wide primitives. So when you have values in GPU memory and you want to do something like a scan or sort or reduce, not in a segmented way, but truly across the entire sequence, we have primitives exposed by CUDA parallel for doing those very efficiently. CUDA parallel also leverages some of the awesome work happening in Numba and the Numba CUDA target. It provides these algorithms and custom iterators, kind of similar to what you have in iter tools, to write extremely flexible Python code for the GPU. You can see an example of using CUDA parallel here with a custom data type. This is translated under hood to a custom number type, and CUDA parallel is able to consume values of that number type and operate on them. Okay, so how can you get involved with CUDA cooperative and CUDA parallel? They're both open source libraries, and they're part of the CUDA Core Compute Libraries, or CCCL GitHub repository under NVIDIA's GitHub. You can just go there and you can pip install both of these libraries. As I mentioned, it should be as simple as doing pip install dot. You can give these a try, file any issues, or even submit a PR for either one of these libraries, which would be extremely grateful for. That's all I had. Thank you all for your time. If you have any questions, I'm happy to take them now.
Thank you for a very nice talk. I'm just going to let people dive in with questions if they want to, because there's not loads of people in the meeting.
Apologies if you can hear the guy on my roof blowing leaves, but a quick question I had. What is the actual problem with PyNV-JIT-link not being available on Windows? Is it like, are there fundamental technical reasons why that can't be provided, or just no one's implemented it in Windows?
Yeah, I think largely it's just been a resourcing and priorities issue where PyNV-JIT-link was mainly developed to support Rapids.
Right, which is non-Windows. Yeah. So what is the plan for removing that dependency that we have on that particular piece?
Yeah, that's a good question. In addition to CUDA parallel and CUDA cooperative, there's a third library called CUDA core, which is Python wrappers around the CUDA runtime and driver libraries. CUDA core is supported on Windows. And so the plan is for this functionality provided by PyNV-JIT-link to ultimately live within CUDA core and for us to rely on CUDA core instead.
While other people are thinking of questions, you showed us some of the boilerplate code that's needed outside of the kernel. Is that something that you can reduce the amount of need for in future? Is it just a case of doing stuff that would sort of support the implementation of that?
Yeah, there's work happening within the Numba CUDA target that I know will help reduce at least some of this boilerplate code. For example, when we decorate CUDA kernel and provide the list of LTOIR files needed when linking that code, I know that the Numba CUDA target already provides some functionality for us not to have to explicitly do that. It can be smart enough to find those pieces itself. Yeah, I think at the moment the API is at a very low level, and really we were we're just trying to experiment and move fast, but ultimately I foresee this user-facing API being much simpler to use and less
Did we lose
boilerplatey.
sound?
Could you repeat the question? I think it didn't quite come across.
I lost sound for a moment, and I was wondering whether it was just me or everybody.
Not sure. Graham, did I come through okay?
Yeah, you did. Any other questions? Okay. How should people get in touch with you if they want to, or where should people look
I think
for
the best
future
place
developments?
for you to get in touch with us is on our GitHub, which is just NVIDIA/CCCL. You can raise an issue there if you have specific questions or start a discussion. We're very active there and more than happy to discuss anything you like there.
And can I ask a short question? Like the CUDA cooperative is also able to exercise, let's say, block reduction with a custom binary operator, which is user-defined in Numba. Is that correct?
Yes, that's right.
So it just allows you to export these cooperative algorithms for arbitrary
arbitrary data
operation.
types and operations, similar to what you can do with the underlying CUB library.
That prompts me to ask about applications. Do you think that this would get used inside Rapids and replace some of the maybe custom C++ stuff with Numba there?
There's certainly, well, it's certainly possible. Rapids specifically needs to support more than just Python as a client. And so mainly for Rapids specifically, I would see it as a prototyping tool or for supporting Python specific functionality. But large parts of Rapids are written in C++. And I don't see that changing because they need to interact with more than just Python.
I have a question about the CUDA parallel, the GPU struct. You said under the hood it is translating into a number type, isn't it?
Yeah.
So can you use the struct types there in the CUDA cooperative operations?
Yes, although I think this GPU struct wrapper is specific to CUDA parallel. For CUDA cooperative, you would define a number type. So I guess like truly a number record type. I don't think there's the need to have this, or I don't think there's a convenience GPU struct wrapper within CUDA cooperative for this kind of operation. Maybe to answer your question more directly, yes, you can do that with CUDA cooperative as well. It's just not as nice as it is in CUDA parallel.
It seems like it's GPU struct should, like Numba should have something like that.
It would be nice if Numba was able to, take in something like a data class and yeah, rather than having to define a record type. I agree.
I'd say that's something we're definitely interested in, and I've talked about contributing to Numba is figuring out, the custom data type support, because we think that that's something that's important, and we've been figuring out the right way to do that, and would plan to engage in upstreaming something along those lines once we've better figured out exactly what the right way to do it.
Yeah. I think for the non-GPU, like for the CPU target, Numba has a JIT class decorator, which has long been a desire for us to support for the CUDA target as well. It's just, yeah.
I would say G class comes with a lot of baggage. You're trying to make it look like a Python class.
Mm-hmm.
Your approach here seems to map closer to just like a minimal C struct.
Yeah.
Okay. That probably will work. It's a lot easier to do. The G class is now a complicated mess. I can say that because I wrote a lot of the code there, so I can call my code a mess. And the struct nature, like the simplicity of a struct I think works better for GPU code. Like you don't need methods. You don't want to deal with inheritance.
I think there's this space to navigate between using something that works like a struct or the struct model in Numba as an extension type, which it sounds like GPU struct does, whereas the CUDA cooperative implementation is using a record. And I presume that's because you want to be able to mutate the data in the record in CUDA cooperative, whereas CUDA parallel, maybe you can get away. I'm guessing that are these GPU structs sort of like read-only once you define them in parallel, CUDA parallel?
Yes, they are. Well, they use the record type underneath, as far as I remember. I don't think they use the struct model, which I think is what's wait, which one is read-only again?
The struct model. I mean, you shouldn't write to it because they get passed by value.
Yeah. Okay, then I'm pretty sure we're using a struct model.
Okay. Yeah.
Struct ref is what I was thinking about, which is the writable type. Is that right?
Struct ref is a writable struct type. Yeah, and that works by being passed around, not by value, but by reference. But we don't have that on the GPU yet, and there's an extra difficulty with reference counting types on the GPU in that when we finish implementing that, we would want to ensure that there's as many cases as possible where the ref counting operations can be elided so that you don't have to spend a lot of time doing that, and to keep actual allocations inside kernels to a minimum as well. I just saw a message pop up in the chat, so I'm just going to check that. Or I thought I did, maybe not. Oh, sorry, someone called Fellow Jitster has their hand up. Would you like to speak?
Well, it's me. So I wanted to ask, although I don't have any immediate applications in mind, whether the CUDA cooperative could work with atomic types if I needed to do a reduction, for example, and I wanted my I think the value be atomic or something like that. I don't know if it makes sense, but
I mean, I guess like one way to implement the global reduction would be to take the results and then atomically add them to some global accumulator. But I don't think I correctly understand your question.
Well, something to the effect of I'm attempting to write, using the cooperative block algorithms, I'm attempting to write in the shared array at location 0 from all different threads, and I want the atomicity for whatever reason, like if I'm trying to implement a histogram or something like this. Then the question is, can that be supported inside the call to CUB, or do I need to sort it out on my own?
I can try answering that.
Okay.
So the input to the cooperative algorithm can be any use-defined type. If you have access to atomic, you can implement something like add operator where you would use atomic, or maybe constructor if you'd like, where you'd load atomically from memory. But if you after implementing a histogram, CUB provides you a histogram that has an algorithm just like block load, cooperative block load, where you can specify that you are interested in atomic block load or block histogram, and then it use atomics internally, and the output histogram is going to be atomically incremented if you are interested in that. So by default, you'll have to wrap data, but preferable ways to use algorithms. Also, the input to this cooperative algorithms is in registers usually. It's not in global memory. That's something to be aware of.
Thanks.
Also, in Numba, we don't have an atomic type as such. We're in the CUDA target, we have atomic operations, but you can't. There isn't like an equivalent of stud atomic from C++.
Thank you.
Are there any other questions or discussion points? Okay, in that case, I think I'd like to suggest that we thank Ashwin for a very nice presentation and wrap up here. Thank you, Ashwin.
Thank you, Graham, and thank you, everyone.